Hello again, everyone. Welcome to Physics Mastery Academy. The diagram below shows some of the equipotentials in a plane perpendicular to two parallel charged metal cylinders. These ones, this and that. The potential of each line is labeled, these numbers. Part A. The left cylinder is charged positively. What is the sign of the charge on the other cylinder? So the left cylinder is charged positively like this. And we want to find out what the type of charge is on this right cylinder as well. The short answer, by looking at the potential values on the left side, we can say that the right cylinder is also charged positively. But let's dive into this answer and find out why it should be positive as well. To conceptually understand this answer, let's start with a single point charge instead of charged cylinders. So for a single point charge, potential at point S located at distance r from the point charge is found by Vs is K times Q over R. Since K, Q, R are positive, then Vs is also positive. For all other points located at distance r from this point charge, the potential will also be Vs, like this. In other words, the surface of this sphere is an equipotential surface. Now let's consider another point, S prime, whose distance is smaller than r, called r prime. R prime is half of r. The potential at S prime again can be found by the potential for a point charge. But instead of r here, we place r prime, which is half of r. And all points with distance r prime from point charge q have the same potential Vs prime, like this. Vs prime can be simplified as 2kqr, but kq over r is Vs. That means Vs prime is 2Vs. And since Vs is greater than 0, then Vs prime is greater than 0. Here we have shown that for the inner sphere, the potential is 2Vs, and for the outer sphere, the potential is Vs. These two equipotential surfaces show that when we go closer to the point charge, the potential increases. In other words, if Q is greater than 0, like this situation, then V increases as R decreases. Up to here, we have answered the question. So we can see that V increases as R decreases. Therefore, the charge on this cylinder has to be also positive, the same as what we have on the left side. Now consider a situation that charge is negative instead, like this. In that case, for the sphere whose radius is R, the potential will be negative because Q is negative. That's why all points on this equipotential surface will have minus absolute value Vs potential. And for the inner equipotential surface, we have minus 2 absolute value Vs. This shows that when the charge is negative, then V decreases as R decreases. And on the right side of here, we don't have such situation. So this again proves that the right side has to be positive, which is consistent with this situation. Please follow part B and part C of this question in the coming videos. Thanks for watching.